So I guess we should get started. So we will probably finish almost whole topic, but still probably left something. At least halfway done for the continuous. So let's since we have been over the weekend, so let's quickly review what we have done so far. So what this topic is about, random variable, just to remind you again what we have been doing is we have a random experiment and the possible outcomes from the random experiment, and for each outcome we put a number to an outcome, right? So, and we also know you can put more than one number, but that would be beyond the scope of a class. We just focus on one number for each outcome of random experiment. I mean, it's easy to imagine that more than two number, right? Say each day the stock market, the stock price for the many stocks. So each stock is a random variable, right? And then it costs you actually no, in terms of theory, there's no difficulties in doing that, but just the math, we do focus on single variable. And depends on what kind of number you can put in, you can divide them into discrete or continuous. For discrete, you just say numbers that usually natural numbers, 1, 2, 3, 4, 5, to put on those, or sometimes you include 0 because you're counting, right? So that would be the thing. And for discrete and continuous, the example there, I mean, say number of head, right? Number of tail, then you become 0, 1, right? And then you told it twice or more times, then you have similar thing, right? Basically, here we have summarized based on one number, right? Just basically makes things more easier to handle. And for discrete random variable, right? We talk about the probability mass function, the cumulative distribution function, and how you can use them to describe the probability. And then later we learn the mean as expectation, right? Is the sum of weighted sum or sum weighted average, right? Weighted by the probability, which is essentially you repeat this experiment many times in your head. And indeed, that is actually the mean of the random variable. Same for the variance, same idea, okay? And I'm not going to go step by step on it. And the important thing is, last time we talked about is there are common discrete distributions. The reason why we talk about those is because later, especially the binomial, we'll be talking it again and again, okay? Today we talk about normal, the bell curve, and the binomial, we'll use it throughout our class. Throughout course would be, I mean, throughout course. And we will not talk about Poisson and hypergeometric, but as you will see, they're very closely with the binomial already, right? You know that, just very briefly talk about this 5 is, right? Uniform is like, just go to the formula, right? Each one is equally likely, right? And binomial is just, there's a one trial of experiment, whether you have success or failure, right? Success is P, failure is 1 minus P. And it's rather simple. And the most general form is the binomial, where you have n independent binomial trials, right? That is something we know. And then that is very commonly used, say Tosin and Con, and so on and so forth, right? And say this question is like, restaurant owner, right? Is a first present like the spicy food, and you just try to see two of them are spicy food. It's a very useful thing because when things can be classified yes or no, right? Then it's binomial, right? It's, say if you ask whether in a election poll you ask whether you support this or not, right? Or you want to ask if someone have disease or not, right? It's binomial, right? Or someone who support this policy or not, right? It's binomial. So binomial, or they have this or not, then it's a binomial, right? So that is very often. And Poisson is asking within time period, right? How many things would happen, right? And you will consider each period is small period, right? Have probably P, right? And you can simplify by saying that actually the probability is related to what we call n times lambda. As lambda is the mean, right? So so that would be the thing very useful is to model number of things happen. Okay, and this is the, I think it's a very useful model. I mean, if you use it to model customer, model number of failure, number of things, right? It's very, that's things we care. And lastly, we talk about hypergeometric distribution. Remember the definition of this is you have n, big N items, right? And A of those are good and M I say are bad, right? So that is what is here, right? That's a N of those, right? A of those is good, M minus A of is bad. You try to take N item out of it, right? And the question is, how many of them are good items? So that's X, okay? And X goes from 0 up to N, okay? And by combinatorics, this is the idea, right? And it's very useful for quality control and audit, okay? I'm not going to repeat, but I hope that would remind you, and hopefully what I have said will be, you can remember. I mean, of course, not the formula itself. I mean, there's no need to remember the formula. The main thing is you would try to see if you are seeing things like you are doing a quality control audit, you should think about hypergeometric. When you try to consider things like two outcomes, right? Polynomial style, there's a binomial. If you try to model something arrival or something happen in the period of time, then it's a Poisson. I think that is something you should take away, or rather than the detailed formula. Of course, detailed formula is good to know, but I'm pretty sure that, I mean, after 1 or 2 weeks, I again probably don't remember. And that's why we don't, I mean, there's no need to remember because now it's easy to check information. I guess it's know how to apply in practice is more important. Okay, so, and of course, we just learned a very superficial of the probability theory, right? So that means if you really want to do more, then you learn much more. I mean, we just focus on the main common distribution, but there will be way more than we have described here, right? Because there are different ways to do things, but these are the most common one, okay? But I think it's sufficient for most business application, I would say. I mean, of course, you're focusing on more technical one, then you will need more, but for standard business application, that would be sufficient. So if there's no question on the discrete, I think the review is short, but I think it's good enough. Let me go to the continuous. Is there a question before we proceed? No. If no, then I talk about the continuous random variable. Okay, just to remind you, what's continuous, right? Continuous means that usually what we mean by is you give a value of the random variable, and the other one, anything in the middle is possible, it's admissible, right? So suppose you say today's stop index, Hansen index, right, is value of like, I don't know, it's like 1600 or 1800, right? Then any value between these two numbers is possible. Okay, so one immediate problem is why we have to define F and big F and small f, but not P. One of the big P is not there, right? You ask yourself why we don't use the same thing for discrete. The reason is being that the probability that the random variable equal to exactly certain value is 0. Right? That is the main reason why we cannot use it. We have to consider case, say F is a well-defined concept. Okay, F is a well-defined, right? Because continuous means, again, you have many value in between, right? So even by math, you know, if any values have been assigned some non-zero number there, add them up, it will be more than 1. Okay. Say if you assign, say the value of, say, Hansen index can be, say, like, right, suppose we have maybe 10,000 to 20,000, right? Any value between them, right? And by continuous, it means that any value in between is there, right? There will be infinite many. There are many, right? Right? Many. So if you assign probability to mean any positive probability between for any value, you add them up, right? Then you expose, right? Because you at most add up the probability must be 1, right? So that's why this is not adding this P of X is not well defined, because any value will be 0. Okay. Do note that any value 0 doesn't mean the adding up together is 0, right? That is the integration problem, right? So there is a math problem is when each value is 0, okay, add them up is not 0, right? That is a what we call the paradox of infinity, right? Say something is what do you mean by infinity? Is like something like this, right? If what we call the probably learn the Chinese philosophy said, right? It's just like you have a stick, okay, 1 meter long, okay. Every time you take half of it each day, right? You never run out of stick, right? Every day is just like 1 meter. You cut it, half a meter, right? You cut it, right? 0.25 meter, and then you keep cutting it. They're still cutting it. You never ever end, right? So there's some issue when you talk about infinity. So the usual intuition for adding doesn't work very well. So that's why we have here need some integration, right? Because here is when we try to add, right, the probability that is less than or equal to X, okay, then you need to have some, it's not summation, because summation is not a well-defined idea here, okay? But I'm not expecting you to know what is actually this means. Unless you want to go further this thing, you can safely ignore if you do not really know what it means, but it means the geometric meaning probably is better to know, right? Maybe I open the. So what this F means the following. X is here. Of course, this is small f. This is 0, right? And there might be some number here, okay? This is called F, okay? And what we are saying here, the integration or the area is like this small f, and that is the big F of A, okay? If A is this value, okay? This area is called big F of A, okay? And the notation, like remember, is what we have, right? Negative infinity to A, F of X D. If you learn calculus, this would be something you know it already, but you don't know, doesn't really matter. Big F, how the big F and the small f related is the area, okay? So the area, right? The area is things we care, okay? Because area tell us what? This is the probability that X less than or equal to A, okay? So that is the main thing we care. We care the probability, okay? And of course, if you are asking the other question is like, what's the probability between, say, A and B, okay? A and B will be just FB minus FA, okay? The reason is same as what you learned in the kindergarten, right? This FA minus FB is the, FB is just this area, okay? FB is this area of FB with this black area. Right, this is FB. Okay. And minus the FA is the, I don't know, red or green, I don't know. I use the red one. Okay. The black minus the red is the orange one, right? So that is the main thing you need to remember. We'll be using it for our class. Okay. And another thing probably you also would need to remember, or you would know, I mean, at the end of the day, is the area, the blue, the whole thing, right? The blue area, the whole thing must be 1, right? I don't know whether I should, maybe I have another tape, put it this way. So this area, the whole thing, okay, must be 1, the area, okay, because the area is the probability of every point possible, okay, and probability at most is 1, you cover everything, right? So that means that the area to the left and the right will be just different by 1, right? So let me talk a little bit about one more, because we'll be using this today anyway, so it's no harm to talk about this again. So we have, so this F, okay, maybe this F, maybe here F, this is the X, right? And this is A, okay? And this area is called F of A is equal to, right? It's the area under the curve, right? It's integrate. And if you learn integration, you will know what's the blue thing, okay? Blue should be 1 minus FA, okay? The reason is being that area under the curve must be 1, because the probability must be at most 1, and that is coming from, and the whole sample space must be 1, that comes from axiom 2, okay? So that would be something we're using, okay? The left and the right add up to 1. Actually, this is also what we call the complement rule, right? Is that clear? Or don't we'll be using it today, and we'll say actually throughout the whole course. So don't worry, you must know it. I mean, it's hard to not to know if you come to the class, unless you you don't do any homework. Otherwise, you must know. There's no way you don't know. Okay, don't worry if you don't fully appreciate what we are doing. Maybe you think this is too trivial, like kindergarten thing, but actually we're doing the kindergarten thing throughout the class, for the whole course. I mean, more or less. Okay, for this style. Now I think I just review you how the big F and small f related, right? And the small f looks like complicated thing, right? and probably don't need to worry about this, okay? And for those who know calculus, you may know the why I have this, because they are actually the same expression, okay? If you know calculus, they're the same thing, okay? That is the how to get f from big F and small f is coming from slope, right? But if you don't learn calculus, then I don't think you need to worry about those, okay? The probably important thing is I let you know how people mention them. This is called the CDF, and this is called PDF. Sometimes they call probability density function or density function for short. So that is something probably you want to remind you what people are talking. Okay. I mean, just to remind, the F is the same as the big F is the same as what we learned the discrete version. Okay. And the reason why I talk about this is no point to talk about a particular value, the probability. So that's the reason. Okay. So if that's okay, then we go. Just because I said, right, for continuous, this is 0. Okay. Again, it means the following 4 things are the same. Okay. Whether you have equal sign has no difference. Okay. So that's why the 4 of them are the same. Okay. Note that this is not true for discrete. Okay. For discrete, this is wrong. Okay. For discrete, you probably can tell me which one is the correct one. Okay. Is the second one is the correct one. Okay. For discrete, this is the second one is right. Okay. Just think about the definition of f of A and f of B, right? F of B is probability that X less than B. This is probability X less than A. Okay. So if you still don't see why this is correct, you move this to the left-hand side, then you see the union of the two is getting you this one, right? Is that okay? Is that clear? Make sure that you understand. Otherwise, well, not very good, because when they ask you less than or equal to, you will confuse, right? Okay. Any question? Okay. And because of the complicated definition, okay, we are going to be easy on the expectation and the variance. Actually, for those who don't learn calculus, okay, this is actually, I mean, or more or less same as the summation sign, okay, adding x, and you can think in your head, x times dx is actually p of x, okay. That is just not loosely speaking, that is almost correct, because if you know the calculus, right, dx is just some interval of x, right? So basically this is you can say this fx times dx is just like px. But if you don't know the calculus, then you can just forget about it, and you don't need to do the calculation unless you care about the proof. But the idea is same as the discrete version. It just consider we repeat this random experiment many times. Okay, you find the average of these outcome. It's just expectation, right? And the variance, again, the same thing. You repeat this experiment many times. Use random variable to translate it to numbers, and then look at how each outcome different from the mean, right? And take a square and get the mean out of that, and that's it. Okay. So there's no, I mean, if you don't care about the formula, there's no difference between discrete and continuous, but of course, continuous it involves infinity. There's some crazy thing would happen. So that's why you need to use integration to make sure that we handle things properly. Okay, and it's okay not to know integration or differentiation because it took human, right? Since they don't math in the early before Christ, right? Before the early days up until Newton, they don't know calculus, right? Even Newton don't very much know the calculus as we know today, right? Not until the very recent 200 years we know what calculus is, right? Because before that, there's no idea of limit and so on and so forth. You learn mathematics, but I think it's okay not to know, okay, for our class. But I hope you know what's going on, okay? Now, I think now we can mention today's goal, okay? What we'll be doing today, we will be talking about basically may not be all, but I hope most of them, okay? We'll talk about uniform, okay? Uniform is something as probably you would learn from the discrete version, right? Discrete is, say, you have a 1, 2, 3, 4, 5, 6 rows of die, and they're equally likely, right? And uniform will be the same idea, just like any number, say between 1,000 to 6,000 is possible, right? Any number between them is possible, it's uniform. And you don't know which one is more likely, they're the same, then it's uniform, okay? And that is very useful. When you don't know what's going on, then it's used uniform. Let's say as a discrete version, right? You have a bunch of outcomes, but you don't know which one to do, then uniform is a first guess to the situation, okay? And the next, we'll talk about more later, but just review what we are doing. What is the exponential, okay? Exponential is actually very closely related to the Poisson, okay? Remember what the Poisson is, right? Poisson means the following, right? Poisson is a case where you have a time interval, okay? Say from 0 to t, right? And you try to cut this interval into very fine subinterval, right? And you cut to n different subinterval, very small, right? And each interval might have an event comes out, right? Might have an event comes out with probability p, right? Say there's an event probability p, right? And Poisson is saying that, okay, the random variable talking about how many outcomes within this time interval, okay? And as you can see, this is a limiting case of binomial when n go to infinity and p is very small, right? Actually, we argue that, right? It is a binomial when n go to infinity, right? And p is very small, right? Then this is a then this NP become a lambda, okay? And that is we call Poisson, okay? And Poisson is the number of outcome that would happen within this time interval, right? Can be 0 up to infinity because n go to infinity, right? So 0, 1, 2, 3, 4, 5, okay? So this number of event in a time interval is a Poisson, just to remind you. Now, exponential is just the following. It's just the first event suppose happen here, okay? And exponential is the time that first event happened, okay? Let me repeat the statement. And there's a Poisson process here. There can be many outcomes, right? That may be happen somewhere or may not be even happening, right? But anyway, the time until the first event happened is exponential, is modeling, is the random variable that follow exponential distribution, right? And as I said, you may not have any event happen, right? So that's why the exponential is any value, the support is just 0 to infinity, okay? We'll be more explicit more later, right? But that is what it means. It's a positive, can take positive value, and it is talking about the time that until the first event happened, okay? And this is the two, and I would say exponential is very useful, right? Because it's modeling time to happen. For example, you're modeling when accident happened for an insurance company, right? And when would fire happen? When would first customer arrive? Okay, these are important, right? Because Poisson just tell you how many customers are going to arrive, right? Doesn't tell you time. But when model time is important, say suppose a restaurant, you need to unfrozen your food, then yes, the time is important. Or you are fast food chain store, you need to cook the potato chips, you need to make sure that it's delivered fresh, right? But you cannot just make it on site, right? You have to prepare it a bit, right? Cannot be too long and too short. So Poisson exponential is a very useful one. Okay, and as I said, that is is a well used in the real life scenario. Okay, this is not something just use it in the textbook, but it actually apply in practice. Okay, and the next one will be normal. Okay, normal probably everyone would have learned it. There's the famous bell curve. Even those who never learned probability would know the bell curve, right? Bell curve is very useful for IQ, EQ, weight, right? Height, okay? And I have often mentioned normal distribution of bell curve is the thing that we are using for many purposes, and actually it arrives, okay? It arrives naturally, right? So that's why originally this normal, the original name is called Gaussian distribution, because it's invented by a very famous mathematician, Gauss. Okay, if you know, this is one of the 4 greatest mathematicians in the math history, right? But anyway, why I call normal? Because it's come up so often. Okay, and in topic 5 or 6, we'll talk about a theorem. We don't prove it, but which we call central limit theorem. I hope this is something will be in your mind. Central limit theorem. And later it is essentially said, if you try to look at measurement, okay, that coming formed by many factors, okay, at the end you will get normal. Okay, we will be more precise more later, but you can imagine IQ is coming from your dad's genetic, your mom's genetic, your grandparents, and so on and so forth, and also the environment, also what you eat, right? Also may also based on what happened in the sky, right? And I know some of you may believe the what kind of month you are born, right? What year you're born, right? This, I mean, how the cosmetic thing, right? Those are all the things that, I mean, affecting your IQ, EQ weight. So that's why you see normal. Okay, so if things are coming from a lot of stuff, okay, I mean, a lot of stuff are determining, a lot of factors are determining your measurement, then it's very likely that it could be normal. Actually, that's a central. That's we will try to. Later, you will see that's why we need it. We happen to use it bell curve that often is coming from a central limit theorem. And why this apply into our class? Because when do sampling, we try to collect, say, sample mean. Okay, the mean, and that turns out later you will see is when the sample size is not that small, this bell curve applies. Okay, so that's why the whole course is based on bell curve, because later after this class we talk about sampling, we talk about doing data, that bell curve naturally arise, right? Because you are collecting, it just mean sample mean is just like many factors together, right? Because it's a many sample, right? Average outcome of many sample, and that is what central limit theorem tell us. Okay, we'll be more precise later, don't worry, but just telling you why the whole course, almost whole course for the rest of after this class, basically we talk about normal almost all the time, besides some binomial when you have discrete, but whenever continuous, normal is something we have. Okay, And even if you ask the binomial thing, I mean, yes or no question, normal would also be useful. Okay, and basically you can say everything we learn for this class is like the bell curve. That will be something take away from this class because you learn how to handle the bell curve. Okay, and probably you ask there's something below, and why I say that we don't learn more than bell curve is because they are just some change to the bell curve. Okay, later you will see when you take square, you get a chi-square. Okay, that is basically what it means. Later you will see, you take a normal random variable, you take a square, then it's a chi-square. And the student t is actually normal over chi-square. Okay, so if you take a normal, this is just normal over chi-square, and chi-square is just normal square. Okay, and f later you will see just a chi-square over another chi-square. Okay, I may lose here. We will define more formally, but so that's why normal is so useful. And probably you ask why we care about those. Later you'll be more clear why, because you use it, you know. Okay, don't worry. But we will give you some meaning to those, and then you see what's going on. Okay. And any question? I mean, it's a little preview, but I hope that will become more clear very soon. So if no question, then I talk about uniform and then probably a break, and then after the break we do exponential and normal. Okay, so let's do the uniform, and then if you have time, we will talk about exponential. So uniform is very simple, and probably some of you may notice my slides may be slightly different from yours because I just change some exposition, but there's no change in the content. Okay, just little bit different presentation, but everything the same. Okay, there's no new material being added besides there's some rearrangement. Okay, so uniform is saying that any value, okay, uniform just try model. The random variable is actually can be any value between interval between A and B. Okay, and is equally likely, so you can't tell which one is more likely. So that's why the support is just A and B. And this technical sense is we don't allow infinity, so that's A and B are finite. Okay, so that is the way we impose. Okay, and I think it's good to, because of uniform, it's good to illustrate what is the probability function and the cumulative one. I want to illustrate these two idea to you to make sure you understand what's going on. So let's quickly, I moved it to a whiteboard here. Okay. So now I have a uniform. Between A and B. Okay. So it means that between A and B equally likely. Okay. So what you would expect from the F for this, okay, F is between A and B, okay, A and B is here. So what I expect? Uniform means that every point is the same, okay. So the F should be a flat one, okay, because no point is higher than other, right? The equal should be equal height. Okay, so we should expect these things should happen, okay? Between A and B. These things should happen, and beyond B should be 0, right? Because nothing beyond B and nothing below A. So look like this, okay. And if you are not comfortable, you can forget about beyond B or less than A because not very important. They are 0, okay. So, and the key thing probably we want to know is how tall is this guy? How tall is this guy? Okay, how tall is this guy? the first thing you remember, you would know it is, let me use, I don't know, yellow color, okay? This area, remember we said the curve under F, the total area must be 1, right? This area is 1, right? Because that implies was this value, this is the probability between X is equal to A and B, right? So it just, what is the probability that the random variable between A and B, and you know, we mentioned is uniform A and B, just like must be, and if A and B is possible, but not outside, right? So the probability must be 1, okay? And now we use our primary school math, okay? The area is 1, okay? And probably you remember how to calculate rectangle, right? It's the base times height, it's the area, okay? Repeat, base times height. So that's what we have quickly. Here, this area, this base, the length of the base is B minus A, okay? B minus A times what equal to 1? Okay, so if you don't, the question is B minus A times what? Let's call this I don't know, Y equal to 1. So what's Y? Okay, Y is 1 over B plus A. So this height is B minus A. Okay, or if you don't fully get the algebra, you can say B minus A is 4, right? 4 times what must be 1? 1 over 4, right? So that is what it is. So that's why we have in the notes, we have the following. If you check the notes, which we don't go back, is this is B minus A if X is between B and A, right? That's otherwise. So that is what you see, because when between A and B is B 1 over B minus A, and out of it is just 0. Okay, so that is how we get the graph like the uniform. Okay, I hope this try to make that you understand why we have this one. Is that okay? Is that a question? I mean, of course you are not, I'm not, since I don't put the notes, I'm not assuming you to reproduce this all the thing in the assignment or the exam, but just let you know how you get it. Okay, just give you the idea, you get it. Okay, so don't worry if you don't fully follow, but I try to give you some idea what's going on. It's good to know, of course. I'm not expecting you to reproduce this in your exam, so don't worry. Okay, is that okay? So let me talk about this big F and then have a break. We'll quickly talk about the big F. Okay, let me repeat what we have here. Okay, this F is here. A and B is uniform. Okay, and we have this height. This height is 1 over B minus A. Okay. Now the question would be, what is the big F? Okay. What's the big F? What's the big F? Okay. Big F, let me use another color. We have A here, we have B here. Okay. And okay. So first, what should be the f of b? Okay, f of b must be 1, right? Because you will say uniform between a and b, right? Is the value must be between a and b, right? And f of b is asking what? Just to remind you, is the probability x less than or equal to b, right? That means that must be 1, right? So this, if I 1 here, okay, it must be here, okay? And beyond b is also 1, so we have that. Okay. And similarly, you can see what is f of a. F of a will be 0. The reason is being that the probability that x less than or equal to a is 0, because you cannot be anything below a, and probably you may be worried about equal to a, but when they're the same thing, right? Because the same thing. Okay, so that's why you would have this thing would happen. Okay. Now, probably you ask what is the value in between? Okay, so the question is actually not that difficult. Okay, so suppose the value x is here. Okay, what should be this value of f of x? Right, f of x is asking the what? Probability that x is less than x, right? So what is this f value? Should be just x here, right? And this area, right? This area will be the f of x, right? This area is exactly f of x. Now the question would be, hey, what's f of x? What's this area? Go back to our primary school. Rectangle is the base times height. What's the base? The base is just x minus a. The height is just b over a, right? So f of x is just x minus a over b minus a. Okay? So you can check this is linear in x, right? F of x is linear in x, right? It's a linear line of x. Linear line, you know the 2 points, you just join them up. That's it. Of course, you can check this is correct by picking any point. That would be what we want. Okay. Of course, I say linear, and then you know the 2 points. It's a straight line. Okay. If you learn calculus, that will be easy. But I mean, suppose you don't know calculus, then that is how you derive this one. Again, I repeat, I'm not expecting you to reproduce this in your homework, your assignment, your exam, or whatever. Just need to know what's the big F and small f. Okay, you know it. Okay, there's no need to panic. There's no math class. Okay, probably this is the only thing we do the F and big F. Okay, we're going to do this once. We're not going to talk about exponential thing. Okay, this is only time we do this graph. Is that okay? So we're not going to do anything about it. Okay. If you do, someone mentioned integration. Actually, you do integration, you get this function. You do differentiation, you go back to this one. But we're not doing any. Complicated. You just do simple high school, or say actually the primary school math here. Okay. So don't worry if you don't know, because we're not asking you to reproduce that. Okay. What actually you know is if you apply, it would be just applying this formula. Okay. This is the formula that we need to know. I mean, of course, you can forget about the integration. This is the thing. Okay. This is the formula you need to, and we derived that for you already, right? Just know we just derived that. Okay. And let me quickly go to example, then we'll break. I'm sorry if a little bit longer, but I think it's good to know what's going on. And it's not terribly important, but probably you might guess the mean would be A plus B over 2. Okay. The value is uniform between A and B. Okay. And any number is likely. So what's the mean? Just at the middle, right? Because anything is possible. Exactly middle will be the mean, right? Just because this is just mean that, right? Just to remind you quickly, if between A and B, right? The middle point is just A plus B over 2, right? Just the middle point, okay? And the variance, we don't prove it, but you can see the variance is proportional to the interval length B minus A squared, so which is very natural, right? The larger and the smallest, okay, the bigger the interval, then the variance will be larger, right? And you have square because you have variance, right? Everything is square, okay? So that is, and divided by 12. To be honest, until now I don't have a good reason why it's divided by 12, except I tell you to follow the calculus. So I don't have a good reason to explain to you for this one. If you know how to explain 12, let me know. But so far I don't have any success to give you the idea of 12 after a few years of teaching of this one and 20 years of learning. I don't know why we have 12, but this is what it is. So, and if you know, you can think about a good reason, let me know. Okay. So quickly, this is the graph. I think we have already said if A to B is the distance 1, this is 1 over 1 is 1, right? And if you have span over length of 4, the F is just 1 over 4. Okay, so this is not very important. Just to show you this is the graph, we have known it already. So let me very quickly go to this example, just applying. Okay, so there's nothing new here. If a rainfall follow a uniform distribution between 1 mm to 4 mm, what is the expected daily rainfall, right? This would be the A, this would be B, right? This is A plus B over 2. This is B minus A over 12. So it's just applying directly to the model and predicting the weather, this kind of thing. I mean, using uniform is perfectly fine, unless you want to have a complicated model, right? You don't have a complicated model, uniform would be the best thing to follow. Unless you know how the cloud is moving around, then I think uniform is one of the easiest thing to handle the situation. Of course, people from geography may disagree, but with B school, I think it's okay to assume that. I think we have the question here asking what is the same question, but asking what is 1 mm and 3 mm, okay, the rainfall, okay. So just to remind you what the question is, A is 1 mm, okay, and 4 mm here, okay, and we know that just to make our life easier, we just don't do the mm, okay, just make it 1 to 4, okay, and what I'm drawing is the small f, okay, and the distance of this is actually 3, okay, and that means that this height is 1/3, okay, so this is maybe I say, okay, so the question is asking what is the probability between 1 and 3, right? So basically just what is given is up to 3, okay, and what's this area, right? Because the probability between 1 and 3 is the area under the curve f between 1 to 3, right? That is the meaning of f. right? So this area, okay, is this probability. And then can be less than 3 because less than 1 has nothing. The reason is because this is 0, right? Because you can say minus x less than 1, and there's nothing lower than 1, so that is 0, okay? And that means that we can apply f of 3, right? And the formula is, remember the f we have derived, f of x is just x minus a over b minus a, and a in this is 1, and this is 4, and this is 1, and x is 3, just put it there, then you're done, right? But you also actually know from this primary school math, right? The base is just 2, right? The height is just 1/3, so it's 2/3, right? So this is very simple. Okay, of course you can apply the formula or you can do the graph. Okay, it's also, I mean, it also works, right, for uniform, because you know exactly what the graph looks like. It's just you can calculate the rectangle, right? But if the f is irregular, calculating the area will be very painful. You need integration, but we don't need that. Okay, I don't need to do that. I mean, okay. Sorry, just give me a little bit more, 1 more minute, I guess. Sorry, a little bit, because I want to, and this we'll soon have a break after this one. Okay, so sorry, because I want to some continuity over here. So here the same question, but instead of between 1 and 2, we ask 2 and 3. So the question is very simple. It's 1 and 4 again, the question, right? And you have the height. Okay, and this is 1/3, right? So the question is asking what's probably between 2 and 3. Okay, so it's asking between 2 and 3, what is this area? Okay, so the first way to do it is using the primary school math, right? The base is 1, the height is 1/3, so the answer is 1/3. Okay, but also you can use the technique we learned. Between 1 and 3 is between 3 and 1. Okay, here I just being lazy, I should use less than, but it doesn't really matter for continuous. Okay, I just jump a little bit because it should be equal to this guy, right? But they're the same. I just jump by 1 step. Is that okay? Because they're the same. And this is f of 3, this is f of 1. Okay, so that's why you just apply, remember the f is just x minus a, b minus a is the big F. Okay, and here remember a is 1, b is 4, so everything it goes. Okay, so don't worry, this is the only chance you are going to calculate, I mean, looking at the f and big F. And exponential and normal, you never look at the f and big F again. Okay, this is the only chance you look in the f, because you need to know what does it mean, right? So let's see this simple one. Okay, let's a break of 10 minutes, and then we come back, we'll cover exponential and normal. Okay, if I time, we cover t by Poisson and those t and chi-square, those kind of stuff. But let's a break of 10 minutes. I'm sorry for a little bit late for this one, but let's a break. I'll go around to see if any question.
Someone mentioned the typo here is thank you. The ground is right. Thank you. Not everyone. If I keep updating the now I think my 我覺得點解啦？不過下次你係我樣啦，芒果係個頭啊，冇頭嘅，芒果芒果頭啊，咁啊我唔可以諗嘢，唔可以睇，唔可以即係連得開咗嚟。做一個問題，多啲做啊，咁個Very good question. Sorry. Yeah, copy and paste from the previous line. So small big F is like any number. I think the probability that the random variable small f will cover same I think the area under the surface and the area under the surface. The same thing you learn. And you can consider small and we will not using it. Yeah. we will not do the calculation, just need to know the concept.
So during the break, many people ask me again, what's the big F and small f? So quickly, just to remind you the definition, big F is saying that you give me a number, the big F will give you the probability that the random variable less than or equal to that number, right? Because just to remind you again, right? The big F is the probability that the random variable less than or equal to that number, okay? So the probability, it immediately gives you the probability, okay? And what is this? How about small f? Small f, you have to use integration, okay? So in that case, actually, we do not use it directly. We use area under f, okay? That's integration, right? So we want to say area, say under A and B, okay, is the probability between A and B, okay? So there are difference, okay? For small f, we need to look at the area under the graph. For the big F, automatically gives you a number, okay? And of course, they are closely related, right? You can see because they are also talking about probability that a random variable between certain range. I hope that is clear, okay? Don't worry, as I said, you will be doing this many, many times for class, so shouldn't be an issue anyway, okay? You may confuse a little bit, but when you do assignment, there should be no issue, okay? And I skipped the proof. I think it's okay if you need to, if you're confused with the proof, so just ask me if I can help you out, or you can ask the TA for further help. So I think we can go to talk about exponential, okay? I hope I preview this is very clear what we're doing. For exponential is we have a Poisson thing, okay? And the Poisson have mean lambda, okay? Okay. And we're asking when a first set happen, that is called exponential, okay? And because of Poisson, okay, one very important property that which you may or may not aware is if you have Poisson, that is an important property called memoryless, okay, which said regardless of how long you wait, okay, the probability is the same. Okay, so what does that mean? Okay, let me give you a more clear idea. Okay, suppose you're waiting for your girlfriend and boyfriend or your friend at somewhere, okay, they're going for dinner, okay, and your friend is known to be a latecomer, okay, so you would expect, suppose now you make the dinner appointment at 8, okay, so you think that she would arrive for the next 15 minutes, okay, with half of probability, okay, half of the time he will arrive, he or she arrive in the next 15 minutes, okay, and unluckily after 15 minutes he or she doesn't appear, okay, so what's the probability that she or he arrive in next 15 minutes? Same, 1/2. If she didn't arrive, okay, what we're going to do, wait 15 minutes more. Now it's 8:30, okay, what is probability that he or she arrive in next 15 minutes? Half again, okay, so the probability of arrival doesn't change, doesn't be the same regardless how long you wait, okay, So usually you expect things are different, right? Suppose you wait for an hour, you should expect is he or she should likely to come in the next 15 minutes, right? But if it's not the case, then you have some memory, okay? So just let me repeat the statement again, okay? If you want a technical definition, it's like this. The probability that x bigger than s plus t, given x is bigger than s, is same as probability x bigger than t, okay? So that is the formal statement, but I don't think we need it. It's just like after we wait s period of time, when he arrived, t more time is same as original. You wait just t. Okay. In our example, t just 15 minutes, right? Okay. Regardless of how many s waiting time you have done, you're asking t more, always the same. I think it's the same phenomenon when I ask my kid to do homework. And whenever I say, how are you going to do? I do it 10 minutes later. 10 minutes later, you ask him when you do homework, still 10 minutes later. Keep not doing the thing. Okay, keep delaying. Okay. I think that memories fit actually the idea of a looking husband rock. You know that? I mean, there's a very famous thing. I don't know whether the people from the other country would know. It's a traditional story. There's a mountain, right? And there's a rock there looking at the sea. Usually a woman, looks like a woman, and he keep looking, waiting for his husband to return. I mean, never return and become a stone, right? There's a famous 望夫石or 望妻石, whatever, right? Just keep looking. I mean, why? Memoryless, where every day he go, right? Suppose it's not memoryless, right? In that case, he or she should leave, right? After 10 years, right? Should expect, I mean, it's gone, right? Right? So that is one famous, I think it's good to look at that story, right? I think that's one, I don't know whether you guys would know. There's a famous story in Chinese, I don't know, 武侠小说, there's a one guy, okay, and he only had one hand because the other hand is being cut off, right? And then suddenly, I don't know, for some reason, his wife dropped off the cliff, okay, and he also want to drop off, but his friend told him that no, your wife will return 16 years later, okay? And then after 16 years, she did not come back, and he jumped to the cliff again, down, okay? If you know, it's Yang Guo. So why? Because the process is not memoryless, right? After 16 years, she gave up the hope that his wife is coming back, right? If if ever he believes memoryless, right? Then he'll keep waiting and waiting, right? But no, after 16 years, he gives up the hope that his wife is going to turn back. So that's why he jumped down. But of course, the end story is none of them die. But of course, the only story anyway. But that is the modern memoryless, and then you can see this need not apply for many process, but as same as Poisson, that is the most useful one. Okay, I hope I convince you waiting thing, right? Memoryless, and I think it's good to talk about why it's called exponential. Okay, the reason is, of course, probably you don't need to worry, is it's the f according to Poisson looks like this guy. Okay, and as you will look at this, looks not familiar, but if you remember exponential Poisson's like this. Okay, so they have E here, the same have E here. So it's very similar, but of course, there's some math reason why this is working. I'm not going to explain. If you want, you can check. I think the slide, I think I have some explanation, some discussion, but this is the small f looks like. And why it's called exponential, as you will see from the next slide, is actually look like this exponential means the exponential decay. Not very good, but look like this. The f look like this. Okay, you will see from the next slide, that's called exponential. And if you learn physics in the high school, then that is what the you learn radioactive nuclear thing, the physics, right? That is exponential decay is exactly what's going on. Probably you would know later if ever Russia trying to release the nuclear bomb, then you know. But that is the exponential thing. Okay, it's like a going down like this way. So it means that it's a highly skewed distribution. So most likely that you will be concentrated at the beginning. Okay. The only thing you need to remember, you don't need to worry about the F, but the big F, the thing you need to careful is this guy. Okay. This is the thing you'll be using. Okay. You'll be use this one. Okay. And this one you don't need to worry, right? Because you don't need to worry about integration. Okay. So just F and 1 minus e raised to the power negative lambda x. Okay. And do note that the lambda, okay, is coming from the Poisson. Okay. The Poisson, the lambda is how many things that would happen in that period of time. Okay. And it turns out this lambda is related to the mean. Okay. So why is mean of x is 1 over lambda? The reason is the following. Suppose during the period, right? Suppose lambda is 2. Okay. That means that within the interval, you expect 2 success, right? Or 2 event. Right? Or 2 event. Depend on whether you want to success or 2 events, right? Okay. So maybe within the first, maybe the easiest, you mean okay, within an hour, 1 hour, okay, you have 2 events happen, okay? So what is the first time you get an event, right? You expect 2 would happen. So you expect half the time, right? 1/2 the time, you should get a first event, right? And the other half, you'll get the second event. So that's why 1 over lambda. Is that clear? So we expect, say, 2 events happen in an hour. So you should expect the first time you get the event comes in is the 30 minutes. All right? Suppose you expect in an hour, you have 3 events comes out. So the first event will come out in 20 minutes. Right? The second one, of course, 20 minutes again. Right? Do remember we talk about the time until the first one, right? But because memory with us, we just need to consider the first one, right? Because the second one will be the same thing, right? So the first one you take a half an hour, the second one will half an hour, right? Because it doesn't matter how long you have wait. It doesn't matter whether things have been happened, right? If not happened, then the first one, another thing to happen will be the same, right? So I'm not going to prove it, but the variance will be a square, which again, I don't have good intuition for that for you, except the proof. So I'm not going to talk about that, but that will be the mean and the variance. Okay. Do note that a little bit different is the when you have Poisson, the mean and variance are the same, but the exponential is not. Okay. So this is, I think this is the 2 formula that you might directly use it. Okay. And also the F, right? The big F is 1 minus e to the negative lambda x. Okay. So these 2 are these 3 are the formula that you might want to use it. Again, you don't need to remember because it's a one book. You remember where to find it, and it's fine. Okay. Is that okay? Now we see the example, then you will see how they're being used, and I would say you will find it useful. As I said, this is look like when lambda is this, right? Lambda is this. 1 over lambda is 5. Okay. So this guy. Okay. For this guy, this one. Okay. You see from 5, this graph is like a lot of things is before 5 already, right? Because beyond 5 is going lower and lower, right? So most of things actually happen before the mean, right? And this is 1 over lambda. Look at this one, right? So many things are happening here. All right. So, so you expect the median is way before 2, right? Because it's way highly skewed. Okay. 2 is the mean, all right? But the median will be, look at this area, right? The median probably something like this one, right? Median something like way before it. We don't prove the median thing, but that would be likely to have much earlier. But anyway, I don't think this is important graph, but just let you know when you see this exponential, this why we call exponential, right? This is exponential because it's like fall down like an exponential drop. Okay, but that is the reason why this is called exponential. But I guess it's good to look at the example. Okay, so this example is rather similar. Okay, well, simple is like we have a customer to arrive, okay, follow exponential with 20 minutes, okay. Again, you would ask how I get this 20 minutes. Look at data, okay. Look at on average time that for a customer to arrive, okay. That's 20 minutes, and arrival time. If you think that memoryless is a good thing, then it's exponential. Indeed, although I didn't show you, actually you check a textbook. If you try to model time arrival, if you require it to be memoryless, it must be exponential. There's no other way around. Okay. So if you want memoryless, exponential only choice. There's no other choice. Okay. And now the question is being what is next 10 minutes? Okay. So just to remind you what we are doing here is X, there's F, okay? There's something like this, okay? This is 20 is the mean, okay? The question is, next 10 minutes, what this guy? Okay? So this is the question, okay? And we know this area is exactly F of 10. Right? Because from 0 to 10, right? F of 10, less than 10, okay? And we know that the mean is 20, okay? Mean is 20 minutes, okay? So mean is 1 over lambda, okay? Because this is 1 over lambda, okay? So that's why lambda is 1 over 20. Is that okay? And remember, f of 10 is 1 minus e to the negative lambda x, okay? And x is 10, so this is 10, right? Lambda is 1 over 20, okay? You put it the number there, you will get 40%, okay? So it's rather interesting, right? Because you expect 20 minutes, someone to come in, right? On average, right? But actually, 40% of people actually come way much earlier, right? Halfway is done, okay? If you believe that exponential. Okay, so is that clear? Is that okay? So there's nothing very deep here, but except applying it. And I told you that if you believe memoryless is a good thing, exponential is the only choice you can do. Okay. Is that okay? Again, I add another. I think I add another one. Is with the same question, but instead asking within 10 minutes, we're asking next 10 to 15 minutes. Okay. So this is another question. So let me quickly draw this again. So exponential, f here, x here, is between 15 to 5. Okay. So this is the area they want to find. Okay. And this is the probability we want to find, right? It's exactly this guy. Maybe I use the red color. Something we want. Okay. And but we do know how to find this guy, right? But we do know two things. Okay. We know the blue area. Okay. Blue area is coming from f of 5. Okay, because it's less than 5. Okay. And we also know the green area is f of 15. Okay. So red will be equal to green minus blue, right? Green minus blue is red. Okay. Green is f, right? F just apply, right? Because just very simple, right? 1 minus e to the negative 15. Sorry, lambda is 20, right? Lambda over. Okay, because we have the reason, because the formula is like this, or f of x is 1 minus e negative lambda x, and lambda is 1 over 20, same as what we have just done. We just did, sorry. So that's how you get the F15 and F10. I don't think you have any issue. It's just like 1 minus e to the negative 20 times 5. So any calculation will give you the answer. Okay. Is that okay? And you see, you might need to type a lot of calculation in the calculator, but later when you show Excel, basically you can just do it by one step. Okay. Excel have already inbuilt all these formulas. You will later see you'll be very fast. Just type in exponential date and then you're done. Okay, so don't worry. You look at the slides afterward, you see Excel can do it very quickly. Okay, so there's not an issue about using your calculator and do the exponential thing. Don't worry. You don't need to, because Excel do it quickly. Okay. Any question? Any question? Okay. I hope that I convince you that the exponential, that's one of the most useful thing when you model time, because normal is not a good one. Okay, why we are talking about exponential? One of the things is that normal is not a good model for time. Later you see the bell curve actually extend from negative infinity to positive, a lot negative number. But at time, you shouldn't allow negative number, right? So that's why that's why we still learn this, even though I've said normal apply to many things, right? But normal can't talk about have to include negative, right? So this is not very good when you talk about normal. But of course, if you the number is large enough and then things are okay, then normal will still be okay. But anyway, that would be another topic. Is that okay? If no, then no. Okay. Then we will finally, sorry, I jump a lot, but I think it's okay to skip unless you have a question. Okay. So now we go to the very last, the thing I want to talk today is some introduction to the bell curve. You will take another class to finish everything. But I think the bell curve, we can finish the introduction. Okay. So normal distribution, the bell curve, okay? And as I explained, this bell curve is so common, and we will have use it for IQ, weight, high EQ. This is a very common, I argue already. And you look at all these crazy thing appear here, okay? The question is, do you need to know it? No. And even I can't remember it if I'm not working on those. Okay, so why I put it here? Because that's the most important thing in this class. So if I don't put it there, then I will be missing something, right? So, and you'll be using formula, look at the table, later you will see you're not doing any calculation. For those who are good at math, you will notice actually even you are very good at math, you cannot calculate this guy. Okay, there's no closed form solution for this integration. Okay, so that's why I don't have equal to what. Okay, so even you're good at math, you cannot do it. Okay, you have to use computer to do it. Okay, so don't worry about it. Okay, I just put it there for it to be complete. Okay, but do notice exponential with lambda, right? So I have one thing to control. For this one, we have two things. Okay, mu and sigma square. Okay, same as binomial of n and p, right? So this one has mu and sigma square, and immediately you will ask why you pick mu and sigma square. Exactly, it is mean and variance. That's why we pick exactly the symbol mu and sigma square. It's exactly, and even though I don't want to go to this, but here you will see one thing, hopefully you can see, is this F, okay? Why called bell curve? There are many things, okay? Exponential looks like a bell, but one thing is actually this exponential, right? So that's why it look like this, right? And this is the mu. That's why it will be look like this. And why it is a one thing, the bell curve is symmetric about mu, right? Look at this one, okay? This is unrelated to x, right? Some constant here. This is some constant here. Look at this is minus mu square. So which means that if you look at the mu is here, above more than mu or less than mu, okay, this would look the same. So it should be symmetric about the mu, right? And then you learn it's e to the something, that's why it look like this. Okay, but anyway, I don't think we need to know why it look like bell curve, but one thing draw from this f function is, the first thing is it will be symmetric about mu, which I think I put in this symmetric about mu. Okay, that is so that means that if you actually is a symmetry, so that's why if you look at the skewness, then it will be 0. Right? You have to calculate skewness, it will be 0. Okay, and so you don't need to worry about this. The only thing you need to know, right, is this one, right? Mean is mu, variance is sigma square. Okay, that is not saying nothing, but this mu and sigma square appear like this way. Okay, this is different from we call the mean is mu, the variance is sigma square, but actually it's referring to this too. Okay, and want to illustrate what the bell curve looks like when you change mu and sigma, right? Because in this model, we're not going to solve this guy, right? We'll look at this guy, and actually, but still, this graph is very intuitive, okay? Because mu and sigma are exactly the mean and variance, okay? So we try to see how different mu and sigma would change the shape of the F, okay? So first look at, let's compare the graph between red and green. Okay, look at the red and the green. Look at the red one and green one. What did you see? Okay, what did you see? They have the same mu but different sigma square. Okay, so By definition, they're the same mean, but they have different variance. Okay. And what do you see? The bell, the peak of the bell, okay, is located at 0, right? That is the normal, right? The normal one thing is the bell, peak of the bell is also the mean, right? So the first thing you know from this diagram is this one. The second thing you know from comparing these two is area under the curve F is always 1, right? So if the red curve have higher variance, more spread out, right? Both than 1, it means that it must squeeze a little bit downward. Why? Because imagine the following. I hope everyone have played a dwarf when you're young. Play dwarf, right? So, or I don't know, you pay whatever thing. Pay dwarf is just like you no matter how you push it the same volume, right? So if you have a mountain here, right? You want it to more spread, you just press it, right? You spread out. So that's what you mean. Okay. From the green one, okay, you have the same area, you press down, then you just spread out. So that's how you get it. Okay. So increase the variance, we're getting more spread out. You just imagine you have a big hammer and smash, and then that will spread out. Okay. And now you want to, is that okay? So increase variance, get more spread out. Okay, without changing the mean. So you can say the mean and variance are independent, right? Mu control the location. Okay. Sigma control how it spread out. Okay. And you compare the now let's compare the blue and green. Okay. Blue and green have same variance, only the mean is different. One is -4, one is 0, same shape. So as I said, mu is just pushing or pulling around without changing the shape. Okay. Mu is just location, sigma is the shape. Okay. So it's very simple. Okay. So in this particular case, mu and variance separate. Okay. So that's different from many things we have studied, right? For the Poisson, mean and variance are related. Exponential the same. Okay. Binomial the same, right? Normal is the same. I mean, they're related, right? But here we have say you can have a separated mean and variance, right? Increase mu, move it around, right? And increase or decrease sigma, then you will be smashing flatter or taller. Okay? Is that okay? And I think I stop here. We will talk about the rest in the next class. Okay. Thank you. I'll see you on Wednesday.